Welcome. So the topic we will be discussing in this lecture is execution of a complete instruction. So basically we'll be discussing three concepts. First we'll be discussing execution of a complete instruction. We'll take one full instruction and how it gets executed by the computer, by the basic processing unit or the central processing unit. In step by step what happens, that is what we are going to discuss. Okay. So this is the first one we'll be discussing. Followed by this, we'll be discussing like how a branch instruction is getting executed. When there is a branch, the normal flow of the program will get disturbed. Okay, so how that is being done. This is the second thing which we'll be discussing. So for the first two things, that is execution of a complete instruction and for execution of the branch instruction, we will assume that the CPU, I mean the processor or the CPU is having only single bus architecture, which we have already discussed. So this architecture we will consider. Okay, so considering this architecture where there is only one internal bus, if you see there is only one bus, then how these two things will be done, that is execution of a complete instruction and how branch instruction will be done. That's what we'll be discussing in the first uh, two what you call subtopics which we are going to discuss in this lecture. And the third topic what we'll be discussing is something called as multiple bus organization. In that, what will happen in the sense, instead of one bus we'll be using three bus. Okay, instead of one bus we'll be using three bus. So for your clarity I'll show you that diagram. uh, so there will be three buses. You can see this diagram. Here there are three buses, bus A, bus B and bus C. So what is the role of all these buses, and when multiple buses are there, how the efficiency increases? We'll be discussing that with the execution steps involved for a single instruction, right? So these are the objective of this particular lecture, right? So first we'll be discussing execution of a complete instruction using single bus organization. Next we'll be discussing execution of a branch instruction using single bus organization, and then we'll be discussing multiple bus organization, how multiple bus organization improves the efficiency. That we'll be discussing through one example, right? Okay, let us start. So first we'll be discussing the execution of a complete instruction in a single bus organization. So this is the instruction which we are taking. So we'll be seeing step by step how this is getting executed. So the instruction is add R3 comma R1, but R3 is given within bracket, which represents that it is a memory indirect address. Okay, so R3 contains some content, right? Say if R3 is 2000, then it means that it refers to the value at location 2000. Okay, so in memory there is some location called 2000. Maybe this location may contain some value. Okay, this location may contain some value. Say it is 15. So what it says in the sense, the content of this location 15, the content of this location 2000, which is 15, should be added with the content of R1. Okay, let us assume R1 contains R1 is a register. Okay, R1 is a register. Let us assume it contains the value 20, right? So basically this instruction says that the content of the memory location 2000, which is 15, should be added with the content of R1, which is 20, right? And the result should be stored in R1. Okay, finally R1 will hold 35. So that is the final outcome. Okay, but what are the steps involved in that? That is what we are going to understand. So briefly, these are the steps. First, fetch the instruction. This instruction will be originally available in memory. Okay, so from memory this instruction should be fetched and it should be placed inside the processor, inside the central processing unit. There is something called as IR, instruction register. So there this particular instruction should be placed. Okay, then what should we do? Fetch the first operand. What is first operand? First operand, actually it is an indirect address. So it refers to the contents of the memory location pointed by R3. Fetch that and store it in some temporary register. In the CPU we have some temporary registers like X, Y, Z, right? In any one of that register, that value, the value at the location pointed by R3, okay? Right, so that value will be stored in some register, some temporary register, okay? Then perform the addition. Okay, R1 is, where is R1 available? R1 is already inside the CPU only. Okay, R1 is a register. R1 is already available inside the CPU, and and it is understood that already R1 contains some value. Okay, so in our case it may be 20. Okay, so this is X. This is X. So X may be 15, maybe 15. So this 15 you have to fetch, but you need not fetch R1, okay, because because it is already in the inside the processor only. Okay, so in memory location 2000, you have 15, right? So that 15 is fetched to some temporary register, right? Then perform the addition, add these two things, and store the result in R1, load the result in R1. Okay, so finally R1 will be having 35. So these are the steps in brief, what are the things to be done, but exactly how processor manages to do that, that is what we are going to understand, right? Okay, so this is the system bus organization which we are taking into picture, or this is the architecture which we are using. So it is the same architecture which we have discussed previously, there is no difference, the same architecture. Okay, so uh, okay, so or this architecture, both are same, there is no difference in that, this is only the representation is different. Okay, so basically it is a single bus organization or a single bus architecture model. Okay, so these are the steps involved. Okay, let us try to understand what is that. See, normally whatever the uh, whatever the address of the next instruction, that will be stored where in PC. Okay, so this is the instruction which you want to execute, this is the instruction which you want to execute. Let us assume that this instruction is available in the address 2000. Okay, so the next instruction will be available in the address 2004. Okay, so now this instruction is not yet executed. Okay, so currently PC will point to this instruction 2000. Okay, and during execution of this instruction itself, PC will increment. How that happens and how this instruction successfully executes, that's what we are going to discuss. Okay, fine. So let us assume currently PC is 2000, that is just the previous instruction, the instruction before this add instruction, say that is in location 1996, that instruction has just finished. Okay, that instruction has just completed, so currently PC is holding 2004. Okay, now this instruction should be first loaded into IR. So how we are going to do that? So what we are doing is PC out and MAR in. Okay, what is PC? Here you see PC. So PC, what we are understanding, PC contains what? 2000. Okay, it's not a, there is no address. PC contains this 2000. Okay, that is the address of the next instruction to be executed. Okay, so so what we say, PC out. PC out means what? Whatever that available in PC, that will go out to the internal bus. Okay, so now this internal bus is now holding this address 2000. Internal bus is holding the address 2000. Okay, and then what instruction we are giving? MAR in. So where is MAR? This is MAR in. Okay, so whatever is in internal bus, that will be stored, transferred to MAR in. What is in internal bus? 2000. So this 2000 will go into MAR. Okay, in represents input to MAR, memory address register. Okay, then we are saying read, so this is the lines through which MAR and MDR are connected with the system bus. Okay, so MAR is connected through the address lines and MDR is connected to the connected through the data line with memory system bus. Okay, so because data can be moved in both the direction, from CPU to memory and from memory to CPU, so it is in bidirectional, but address only which, from which address we want, like that only the CPU can request. Okay, so that address was being sent here, so this is only this direction. Okay, so now what it says in the sense, the read read the instruction stored at location 2000, that was given, read. Okay, so what is the instruction stored at location 2000? Add r3 comma r1. Okay, but memory read will take some time. It may not happen in one clock cycle. Okay, so it gives the read instruction and it waits, and it waits, and during that time, actually literally processor will not wait. So meanwhile it will perform some other operation. What is that? Select 4. Okay, select 4. Select 4 means in this multiplexer, top of ALU there is a multiplexer. Here 4 is selected. Either you can select Y or 4. If you select Y, the whatever in Y will be transferred to multiplexer. If you select 4, this constant 4 will be transferred to multiplexer in turn to A. Okay, here also if you select Y, Y will be transferred to multiplexer in turn to A. So now we are selecting 4. Okay, not Y. So this 4 will be available at the first input of ALU, that is the A input of ALU. Okay, next what we are saying is add. Add with what? What is in internal bus? Internal bus is holding 2000. Okay, even though 2000 is moved to MAR, one copy is moved, still currently internal bus is, this 2000 is active. So uh, this is also available in B. Okay, so internal bus is directly connected with B. Okay, so here you have 2000, here you have 2000, right? And this so B's input is now 2000, A's input is 4. Now you are telling add. So add A and B is what? 2004, and that will be available in Z in. So this is Z. So this is input to Z. Okay, that is Z in, and this is the output to Z. Okay, so that whatever the output, which is nothing but 2004, that will be temporarily stored in Z. Okay, right? So what is this 2004? This is the address of the next instruction, because when the current instruction is executing, by that time itself PC should increment. Okay, so this instruction is executing, it is not completed, but meanwhile we increment the PC. Okay, fine. Then see the second, so all these things are happening in one clock cycle, so that this is given as step 1. In one clock cycle, this 1 2 3 4 5 6 operations are happening. Okay, right? So this one instruction, you see, it involves how many operations? Okay, this instruction itself involves this many operations. So now first step is done. Second step, Z out, PC in. So whatever in Z, we are sending it out. Out means what? To the system bus. Okay, so now system bus will be 2004. Okay, not system bus, internal bus. Okay, internal processor bus. So now what will be in the processor bus? It will be the address 2004. Okay, then what we are saying, PC in, that is whatever is in internal bus, move that to PC. So now PC will become 2004. Are you getting? So what happens now? PC is pointing to the next address. Okay, not only that, we are transferring that to Y in also. So whatever in system bus, you are transferring to Y in also. So what system bus contains 2004, we are keeping that in Y in also. Okay, right? Why we are keeping this in Y in, that we will come later. Okay, I will tell that later. Okay, then we are waiting for memory memory function complete. Okay, this previously we asked the memory to read, right? Read the instruction. So it might, by this time it might have been completed or not completed. If it is not completed, it has to wait. Okay, these instructions can be done even before the memory read is completed, but now following whatever the instructions were there, that cannot be done until the instruction is read and placed in the instruction register. Okay, so here we are giving this instruction WMFC, that is memory function complete, let it wait till then. Okay, so if the memory is, if the memory function is completed, it is fine. Otherwise the CPU will wait. But obviously after some times the memory function will be completed, and for which memory function we are waiting? To fetch this instruction from the location 2000. Okay, right? So once it is completed, that instruction, where it will be available, it is supposed to go to instruction register. First itself it won't go to instruction register. We are fetching, MAR is giving that I want whatever the content available in 2000 previously it gave. So that content will be first transferred to MDR. So what is that content? This instruction add R3 comma R1, the same instruction as it is. It will be first transferred through to MDR. First it will come to MDR, okay. Then from MDR you have to transfer to IR, okay, because whenever you fetch something from memory it will come to MDR only. Similarly, if you want to write something to memory, you have to keep that in MDR, okay. So then what we are doing, MDR out, IR in. So this instruction at 2000 is fetched and it is available in MDR. Then we say MDR out, IR in. So from MDR we are keeping this in system bus, okay. MDR out means it goes into the processor bus, internal processor bus. So now processor bus is not holding 2004. Now it is holding this instruction add R3 comma R1. This instruction is in the processor bus, okay. Now from here what we are doing, comma IR in. So this now it will be transferred to IR in, okay. So now IR in will be holding this instruction add whatever the instruction R3 comma R1. So this instruction is now available in IR in, okay. So next what should we do? We should decode that instruction. Okay. So now the instruction is came to IR. So next the instruction decoder logic will decode the instruction. It will decode and it will understand that it is an add instruction, and there are two operands. One is a memory. The first operand is it indirectly refers to the memory, and the second operand and the second operand is actually a register, okay. So this information it will understand and it will generate the appropriate control signal. In this case it is add, okay. So it will create an add signal. So this add will be enabled in the ALU. So it is add, so we have to perform some add operation. So this much it will be done, right? Then what we do, R3 out comma MAR in comma read, okay. So what is this? Because here the first instruction is what? First instruction is a indirect memory. It is referring to indirect memory. Indirectly it is referring to memory. So that content should be read. Whatever that available in R3, that should be read, okay. So if R3 is 1000, then the content stored at location 1000 should be read. Then the content stored at location 1000 should be read, okay. So maybe this content may be 15. So again this R3 content should be moved to MAR. So that we are saying R3 out, MAR in. So R3 contains what? Here all the registers are there. One of the register is R3, okay. One of the register is R3. R3 contains this 1000, okay, which is the address of the content 15, okay. And that goes to R3 out means it goes to the system bus. So system bus will hold now 1000. I mean internal processor bus will hold 1000, and then we are giving what? MAR in. So that will go to memory address register, okay. Then read, okay. But read again it may take time because it is not within the processor. It has to go to memory and it will come out, okay. Then whatever the content available in that particular address 1000, that will be loaded into MDR after some times, okay. But it may take more than one clock cycle, so we cannot expect that to complete immediately. So meanwhile you can fetch the next operand. Next operand is what? R1. It is already available within the CPU only, okay, because it is in one of the register. So what we are doing, we are directly saying R1 out. So R1 out means what? So now MAR is holding 1000 and it has already given the instruction that read the content of 1000, okay. So this 1000 need not recur in the internal bus. So one here what we are doing, R1 out, okay. So here one of the register is what? R1. So R1, let us assume it contains the value 20. So R1 out means this 20 will be moved to internal bus. So now 20 will come here. Okay, R1 out. Then Y in. Y in means so whatever in the internal bus that will be moved to Y. So this 20 will come to Y. Then again we are waiting for the memory function to complete because previously we gave the memory, right? So no, further after this we cannot proceed. This fetching you can do. The second operand you can fetch even if the memory read is not completed, but beyond this you cannot proceed, because next we may want to add. So you cannot add until the first operand is available. So till the first operand is available, you have to wait. So that here we are giving WMFC, that is wait for the memory function to complete. Okay, right? Previously here also we gave wait, because we want to uh, what you call, we want to move that instruction to IR. As long as the instruction is not available, you cannot move, so you have to wait. Similarly here also, as long as the first operand is not available, you cannot add, so we are waiting, right? So if the first operand is available, then proceed, otherwise wait. So anyway, after sometimes it will be available. So once it is available, what we are doing, if it is available, where it will be available, that 15, it will come to MDR. Okay, so from MDR we have to move somewhere else. So this 15 will first come to MDR once the read is done. Then we are saying MDR out and select Y. So MDR out means this 15 will come here. MDR out means this 15 will come here. Okay, right? MDR okay, MDR out means this 15 will come here. Okay, and then so 15 is now available in the system bus. Okay, if 15 is available in the system bus, it will be also available through B input. Okay, right? And then what we are doing, select Y. Select Y. In Y what is there? 20 is there, so this 20 will be available through A input. Okay, so A, through A 20 is passed, and through B 15 is passed. Then we say add. So this 20 and 15 will be added, and the result will be stored in Z through Z in. Okay, input to Z, which is nothing but 35. Okay, but finally the result should be stored where? In R1. Okay, so at last what we give, Z out comma R1 in. So Z out means this will go to internal bus, so this will 35. Okay, and from here we are saying R in. So now the internal bus contains 35, so 35 will be finally moved to R in. Okay, so at last this will have 35, right? So this is how this instruction got executed. So you can see there are many steps involved. Okay, so this single instruction, if you see how many operations it involved, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25. It involves 25 operations. Okay, and it took 8 clock cycles to complete, 7 clock cycles to complete. Okay, right? Right, but still the performance can be improved if you are using, if there are more than one bus. So that we'll be discussing in the third case. Okay, so this is how the complete instruction got executed, which involves multiple steps. Okay, fine. So next we will be discussing about execution of branch instructions, how the branch instructions are getting executed. So whenever a branch instruction occurs, the content of the PC should be replaced with the branch target address. Okay, normally PC will increment. Once after every time. Okay, you see in the previous case, I want you to say one thing. I want to say in Y in also we kept the next address. So initially I said that if this is 2000, the next address will be 2004. Okay, so in step 2, the 2004 we moved to PC, but 2004 we also moved to in. Okay, but later as per this instruction, we updated in with R1 or whatever it may be. Okay, yeah, R1 finally R1 came to in. Okay, but you might have asked why in comes into picture. Why should we keep this next address in in the sense, because most probably you can expect that the normal flow is sequential flow. First instruction, then next instruction, then third instruction. Normally the flow will not be disturbed. In that case the next instruction will be executed will be 2004. Okay, so that we kept that in 2004 already, right? Right, because what will happen then, you need not, next time you need not fetch it from PC directly, you can take it from Y. Okay, that is the reason we kept. Okay, not on, so and most of the time the you may not be using all the registers. Okay, right? or it may be a simple instruction which does not involves any arithmetic operation or any logical operation. In that case, this y may not be updated. But in our case, the previous instruction, it was little complex, because you have to fetch something from memory and then you have to add it with another register. So during that time we needed y. Okay, so we needed y. So even though 2004 was there in y previously, we updated with the content of R1. Okay, right? I think I'm clear. So just if you just understand that uh, y also will hold the address of the next instruction along with PC. Okay. Okay, the reason is when the normally the flow will be after first instruction the next instruction. So from y you can then the next instruction you can directly fetch from y, which will be faster, rather than moving from PC out, then rather than saying that PC out. Okay, or what you call, yeah, rather than saying PC out and then getting it, you can directly get it from Y. So because of that reason, Y was holding the address of the next instruction. Okay, fine. So so actually that Y plays a role here. So that I'm trying to say here. Okay. So what is the role of the Y in the sense? Uh, So in a branch instruction, when there is a branch instruction, the content of the PC will be updated with the target address. Okay. How we get the target address? Target address is obtained by adding an offset. Target address is obtained by adding an offset. Where this offset will be available, the offset will be available in the branch instruction itself. Okay. Target address we will get by adding an offset, and where this offset will be available, offset will be available in the branch instruction itself. Okay, how we calculate the offset? Offset is calculated something like this: branch target address minus address of the following address following the branch instruction. Okay, branch target address minus address following the branch instruction. So this will give the offset. Okay, if the value is negative, then convert it to positive, so that this was added. Okay, so whatever the branch target address, okay, minus the address of the following instruction. Say for example, say we are currently in the location 2000, right? So here there is an instruction. This is, assume this is a branch instruction, branch to some location, say 2050. So this instruction says that you go to 2050 and execute that instruction. Are you getting? Go to 2050 and execute that instruction. The next instruction address is 2004. The next instruction address is 2004. Okay. Now, how we will get this target? What is offset? Here, offset is what? Branch target address minus address of the following address following the branch instruction. What is branch target address? 2050. Okay, 2050 minus address following the branch instruction. Which is the address following the branch instruction? This is the branch instruction. The address that follows the branch instruction is 2004. Okay, so 2050 minus 2004 is what? 2050 minus 2004 is 2046. So the result is what? 2046. Okay, so this is what we call as offset. This is it is not 2046, it is just 46. Okay, 2050 minus 2004 is what? It is 46. Okay, this 46 is called as offset, right? This 46 is called as offset. Okay, this 46 is called as offset. Now how will you get the target address? See, after while executing this instruction, PC will become 2004. While executing this instruction, PC will become 2004, right? PC will become 2004, right? Not only PC, Y in also will become 2004. Here if you see, okay, the Z out goes to PC in and also to Y in. Okay, so Y in also will become 2004. So So I mean the register y. Okay, so y is also 2004. Okay, next what you should do is you just add this 46 with 2004. Okay, add 46 with 2004. What is 2004? Whichever is available in y, whichever is available in y. Okay, select y, and 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 here you have to pass that difference between the branch target address and the address of the next instruction, that is 2004. Okay, sorry, that is, sorry, this will be 46, and through y whatever you are getting is 2004. So this will be 46. Okay, and this will be 2004. Okay, so as a result what you will get is 2050. As a result what you will get is 2050. Okay, and that will be loaded into, that will go into system bus. Okay, and from there it will again get into PC in. Okay, so what will happen, PC in will become 2050, which means the next instruction executed will be 2050. Okay, so this is how actually it happens, right? So in that context we need y. Okay, in that context we need y. Okay, so that every time when you move the, what you call, the next address to PC in, you also move to y in. Okay, right? Because we don't know whether it is a branch instruction or not. Sometimes if it is a branch instruction, then we use y in. For that purpose we use. Okay, fine. Okay, so see, this is the actual usage of in, right? Not it is not that for fetching the next address quickly. Okay, because that is not required, because this is just an address. You cannot, you have to fetch the instruction. For that it has to go to MAR. Okay, so that can go from PC in itself. Okay, so whatever I have said previously, ignore that. Why we keep the updated PC content in in the sense to, because we don't know whether the current instruction is a branch instruction or not. If it is a branch instruction, we use the in, and then we use the offset to get the actual address. If it is not a branch instruction, we just ignore this y. Okay, the y can be used for some, for holding some other operand or whatever it may be. Okay, so that's the actual usage of y, right? Okay, so with that understanding, let us try. Okay, so there are two types of branch. One is called as conditional branch, the other one is called as unconditional branch. Here what we are discussing is unconditional branch. Unconditional branch means there is no such condition, it will always branch. Okay, whereas conditional branch is something like a if some condition satisfies, you branch, otherwise you don't branch. Okay, I mean don't move to that different address, right? Okay, so let us see how the branch instruction is getting executed and the sequence flow of that. Okay, so first so as we have discussed, let us assume this is the instruction that you are going to execute. Okay, so the instruction is, say, branch, I'm calling b, or represents branch 2050. It means go to the location 2050. Okay, say this 2050 contains some other instructions. So from that instruction it wants to execute. Okay, and the instruction that follows the branch instruction, let us assume that address is 2004. We don't know what that instruction is. Okay, it's not required for us at this point of time. So first what we say, so currently, say there is a the instruction which is occurring before 2000 is at address 1996. So let us assume instruction has just completed execution. So now PC will be holding what, 2000. In PC what we have is program counter is holding what, 2000. Okay, the address of the next instruction. So what we say, PC out and MAR in. Okay, so this is as usual, PC out, MAR in, and read. Okay, so what it will do, that previous diagram if you see, PC out contains 2000. Okay, so PC contains 2000, we are saying PC out, so it goes to internal bus. So internal bus will hold 2000. Again you are saying MAR in, so this will go to MAR. Okay, so MAR will hold 2000. Again you are telling read, again you are telling read. So it means that the content of the memory location 2000 should be read, and that will be moved to MDR. but it will take some time because this is memory is not a part of processor, it is external to the processor, so it may take more than one clock cycle. So meanwhile something else can be done. So 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 read was given, but it may take more time. So next, meanwhile PC can be incremented. So what we are doing, select 4, add Z in. Okay, so 4 is selected, 4 is selected here. So if 4 is selected here, through A you will get 4. Okay, okay, and then in the internal bus already what is available, 2000. So this 2000 now will be available through this B input. So in B, through B what you have is 2000. Okay, so here now you are giving add instruction. So this add is enabled, so this 2 will be added, 2000 plus 4 is 2004, and that will go into Z 2004, which is the address of the next instruction. But the current instruction is a branch instruction, so let us see how it changes to the actual branch. Okay, so Z in, then what we say, Z out, PC in and Y in. That is from Z, whatever is in Z, that it goes to PC in and also in to Y in. Okay, so Z out means first whatever is in Z, it goes to the internal bus. Okay, what is in Z, 2004. So now internal bus carries 2004. No more it is 2000. Now internal bus carries 2004. Okay, so this 2004 is now moved to PC in. So PC will become 2004, and also it goes to Y, and also it goes to Y. Okay, so Y also becomes 2004. Y also becomes 2004. In Y also you'll be having 2004. Okay, so this is what is done with the first I mean with the first two statements. Okay, if you see the first two statements, it is same as that of the previous case. There is no change because it is just loading the whatever PC points, that instruction should be loaded and PC is updated, that much only. Okay, okay, then what we are doing, even the third instruction is also same. Third instruction, if you see, MDR out and IR in. So after Y in we are waiting for the memory to complete. Okay, if memory is completed, then MDR out, IR in. So what will be MDR out by this time? MDR out will be that instruction, whatever the instruction. In our case it is branch instruction. Okay, in our case it is the branch instruction, branch 2050. Okay, so that is what will be available in MDR out. Okay, so I mean in MDR it will be available, BR 2000. Okay, so what we are doing, we are saying MDR out and IR in. Okay, so that's what the next instruction, MDR out and IR in. So that will go to IR. Okay, that will go to IR. That will go to IR. Okay, so this instruction now it will go to IR. Okay, that is instruction register, right? See, this first three steps in both the cases, this is called as instruction fetch. Okay, previously also, I mean the current whatever we are discussing branch also, this first three are instruction fetch. Once the instruction fetch, it will be decoded. Okay, now the instruction decode unit will decode the instruction, right? It will decode, and now it will understand that it is a branch instruction. Now it will understand that it is a branch instruction. Okay, so as it is a branch instruction, it will understand that some offset should be added to PC. Some offset should be added to PC. Okay, so the next instruction what we give is, you see here, offset field of IR out, add. Okay, so what is the offset field of IR out? Previously we have discussed how to calculate offset, branch target address minus address following the branch. So what is in our case branch target address 2050? Okay, minus the address following the branch, that is 2004. So 2050 minus 2004 is what? It is 46. It is 46. Okay, so this is the offset. So this offset, okay, offset field of IR out, so this is going out. Okay, this is going to the internal bus, right? So okay, so from IR only that offset field is going out. Okay, maybe this way it is going out. Okay, so what is that offset field? As we discussed, it is 46. It is 46. Okay, now that 46 will be available through B. Okay, now B is not 2000, it is 46. Okay, in A already you have what, 2004. So through A you have 2004. Then next what you are giving, add. So 2004 and 46 will be added and the result will go into Z. Okay, so what is the result? 2004 plus 46 is what? 2050. So Z becomes 2050. So now we got the branch target address. Okay, now what? Z out and move it to PC in. That's it. Z out and move that to PC in. Okay, so Z out means what happens? uh, Sorry, Z out means this will go to the internal bus. So this will become to the internal bus will now go 2050. Then from here it is transferred to PC in. So PC in will become 2050. Okay. So now the branch target address has came into PC. Okay. So this is how the branch instruction got executed. Okay. So for branch instruction we need to add the offset with uh, the next address. Okay, so that next address we are storing in y in. Okay, right. So if it is a branch instruction, this will be used, otherwise this will not be used. Okay, so that's the point. So this is how branch instructions are executed, right? Okay, so the next concept what we'll be discussing is multiple bus organization. If there are more than one bus, then actually the performance can be improved, and the number of steps also can be reduced. If you see that previous case, in the first case there are 7 steps, which is quite what do you say, it is very lengthy, and also the number of operations were more, and it is time consuming. So this can be reduced if you are if there are more than one internal bus available. So this is another architecture where we have 3 buses. You can see there are 3 buses: bus A, bus B, and bus C. Okay, and another important thing is, through PC an incrementer is attached. So using this, PC can be auto incremented every time automatically PC will increment to 4. Okay, you need not add PC again, you again selecting 4 and adding the content of PC, I mean transferring PC to the system bus and then adding. All these are not required. You can directly increment PC, right? So for that this incrementer logic is added. Okay, and from PC whatever the content of PC can be transferred to bus B. Okay, and whatever from bus C can be transferred to PC, right? Okay, okay, and then there is something called as register file, which includes all the registers. Okay, this is actually something like an array of registers. It includes all the registers, and any 2 register content can be transferred to bus A and to bus B simultaneously, or any one, whatever you want. Okay, so maximum 2 register contents at a time can be transferred to one to bus A and another to bus B. Okay, this is if you want to read the content of any register, then you can do this, right? Similarly, if you want to store something in the register, then from bus C it can be written into the registers. Okay, so this will be or in. So this will be or in if you want to write something to the register. This will be or out if you want to read something from the registers. Okay, so if you want to read from A registers, we say or I mean if you want to register from, if you want to read from R1, then R1 out will and you can say to which bus you want, either to bus A or bus B, like that. Okay, then this is the ALU has 2 inputs as usual. One is from multiplexer. Okay, one input for the multiplexer is from bus A, another one is constant 4. Okay, even though for PC incrementing PC we are not using this constant 4, but still we keep this because sometimes some other memory location also we may want to increment. Okay, so in that case it may be useful, right? So multiplexer takes 2 inputs. One is the constant 4, the other one is the input of bus A. Okay, so if constant 4 is selected, then this 4 will be available in A, right? Otherwise, whatever the content from bus A, that will be available in A, right? And bus B, and whatever available in bus B will always available in B, right? And the operation, whatever the operation you perform in ALU, the result will be immediately transferred to bus C. Okay. And here is the IR instruction register. So instruction register is connected with bus C. That is, through bus C only the instruction will be loaded into IR. Okay. And then here we have instruction decoder, which will decode the instruction, and it will generate the appropriate control signal to the ALU. Okay, so here the control signals were not shown. You can assume there are control signals through which the instruction decoder says what to be done, whether add or multiplication or what. Okay, and this is MDR. So whatever the data fetched from the memory, that will be available in bus C, and that can be returned to MDR. Okay, right? If something to be returned to memory, then from MDR it will be transferred to bus A and bus B. Okay, or uh, no, not that case. If from memory, so this is memory, right? Memory is external to the processor. If from memory, if something to be transferred to MDR, that will happen like this. Okay. Similarly, from MDR, if something to be transferred to memory, that will happen like this. Okay. And this is MAR. Uh, uh, so from which address the memory, from which address of the memory the content should be read or write, that will be given through MAR. Okay. So here if some content from the processor should be transferred to MDR, that can be done like this through bus C. Okay. From MDR, so say something from memory you have read. Okay, say some data you have read from memory, that should be now sent to ALU. So that can be done. So MDR can do that. From MDR it can be done by sending that data either to bus A or to bus B. Okay, right? Similarly, from which address you want to fetch the data, so that address should be kept in bus C, and from there it will go to MAR, and then MAR will perform the read, give the read operation or write operation, and appropriately the data will be available in MDR. If it is a read operation, if it is a write operation, the data will be transferred from MDR to the memory. Okay. So this is the brief understanding. Let us see how with multiple bus organization a particular instruction works. See, here there is an instruction add R4, R5, R6. So what we are doing is we are adding the content of register 4 with register 5, and the result is stored in register 6. Okay. So now as we have 3 buses, this can be done in just 4 steps. Okay. So let us see how it happens. Let us assume that this instruction is available at address 2000. Is available at address 2000. Okay. Let us assume the address of the next instruction is 2004. The address of the next instruction is 2004. Okay. So what happens for PC? So the previous instruction is 1996. So let us assume that previous instruction was just completed. So PC will be currently holding 2000. PC will be currently holding 2000. Okay. So first what we say PC out or equal to B. See, here there is one interesting thing. From PC you want the content of PC should go to MAR. Then only you can fetch the instruction. But if you see PC is connected to bus B, from PC you can transfer to bus B, not to bus C. From bus C something can go to PC. Are you getting? But from PC you cannot send to bus C. But actually MAR can take input only from bus C. Okay, so how we are going to transfer this address to MAR? So this is quite interesting. So first what we are doing is PC out. When you say PC out, this 2000 will be available in bus B, right? When you say 2000, this PC out will be available in bus B. Okay. Now it is available. Obviously, it is this 2000 is available in B's input of ALU. Okay, B's input of ALU, right? So next what we are doing is we are the next instruction what we are giving is or equal to A, or equal to B, or equal to B. This is, you can see here, R equal to B. So why we are doing this? Because B contains 2000, so we say that R equal to B. So R also will hold 2000. Okay, so R is nothing but the output of ALU. Okay, so that contains 2000. So it means that now bus C contains 2000. Now bus C contains 2000. Okay, okay. Please, from PC you cannot write to bus C, so that we are doing like this. From PC write to bus B, then say R equal to B, so that it will come to bus C. Now you can say MAR in. Okay, now if you give MAR in, this will go into MAR. Okay, so now we are giving MAR in, so that will go into MAR. Okay, next we say what? Read. Next we say read, because it's a memory operation, so it has to communicate with memory, so it may take some time, right? So let it read that from memory. Meanwhile, what we are doing after giving read, increment PC. Okay, so here we can directly increment PC. You need not add for all those things. In the previous case, if you recollect, again we are selecting for add, these things is not required. Directly you can increment PC. So now PC will become 2004, the next instruction. Okay, address of the next instruction. Next we are waiting for the memory function to complete, because previously we gave a read operation. Okay, if it is completed, then only we can go to the next step. Okay, so if it completes, move to the next, otherwise wait. Okay, so after sometimes it will be completed, then move to the next instruction. Okay, here what we want to do, R4 content should be added with R5 content. Okay, so what you can do, you can move R4 to uh, so first we have to decode the instruction, right? First we have to decode the, first we have to fetch the instruction. Even fetch we are not completed, so after that only you can go here. So first what we are doing, by this time the instruction will be available in MDR. So we are saying MDR out B, because MDR is connected with the instruction is read, and it will be now available in MDR, whatever the instruction add, R4 or 5 or 6. Okay, but MDR, from MDR you can move to either bus B, bus A or bus B. Okay, but here we are just moving to bus B, so that we are saying MDR out B. Okay, so that instruction now available in bus B. This instruction is now available in bus B. Okay, from again from here you have to move to IR, because finally we want to move the instruction to where? To IR. Okay, but if you again, if you see, if you want to move to IR, it should come from bus C, right? MDR is also not directly connected with bus C. From bus C data can be moved to MDR, but from MDR you cannot move to bus C. Okay, so again we are following the same trick. Move that MDR content to bus B. Okay, now the instruction is available in the B input of ALU. It is in the, because in bus B, so it is in the B input of ALU. Now again you give R equal to B. Again if you give R equal to B, that instruction now available in bus C. Okay, so now it is not 2000, whatever the instruction you want to execute, that is available in bus C. Okay, now again you give IR in. Again when you give IR in, that instruction will now move to IR register. Okay, now IR register contains the instruction that is to be executed. Okay, so it will decode, and it will understand that it is an add operation, and what are the registers involved, everything will be understand, and it will give an add signal, it will generate an add signal to the ALU. Okay, now how many registers are involved? 3 registers, R4, R5 and R6. Add R4 and R5 and store the result in R6. Okay, so what we are saying, R4 out A, R5 out B. Okay, whatever the content in R4, we are saying R4 out A means whatever the content in R4, that will be moved to bus A. Okay, R5 out B means whatever content available in R5, that will be moved to bus B. Okay, now bus B contains R4, R5, and bus A contains R4. Okay, so A is nothing but one of the, I mean bus A is nothing but one of the input of multiplexer. Okay, so here R4 is available, right? And bus B is nothing but the B's input of multiplexer, so here R5 is available. Okay, so let me clear everything. So this is R4, so in bus A you have R4. Okay, in bus B you have R5, Okay, So this R4 is now available through the second input of the multiplexer, and R5 is available through B, right? Okay, because this is same, this is available in bus B, so this R5 comes here, okay, right, and this R4 comes here, okay. Okay, now we have to add, okay. Before adding, we are saying select A. Select A. Why we are selecting A? Because multiplexer can take either constant or this A from bus A, okay. So we are saying select A means the content of bus A will be selected, that will be available through the A's input of multiplex ALU, A's input of ALU. Then you perform add, okay. When you perform add, what will happen? The result will be going to the system bus. Here the result will I mean the internal bus. Which bus it will go? It will go into bus C. To the bus C the result will get into, okay. But finally we want the result in which register? In R6. So again we give R6 in, okay. So this result finally will be stored in the register R6. That's it, okay. Then end, okay. So this is how multiple bus organization works. So with multiple bus organization, if you see, the number of steps is reduced, and the number of clock cycles is also reduced. There are totally only 4 clock cycles, okay. So right, so let us stop here. Fine, thank you.